Neutron stars are known for being some of the most extreme objects in the universe. These incredibly dense remnants of collapsed stars pack more mass than our Sun into a sphere smaller than a city, and they can spin nearly 10 times faster. But even these rapidly rotating, densely packed powerhouses have nothing on the weird, wild world of magnetars. Magnetars are a rare type of neutron star with magnetic fields billions of times stronger than Earth's. The intense energy released when these colossal objects form can drive starquakes, massive eruptions of plasma and radiation that blast away part of the star's crust. And it turns out that these sudden blasts may play a crucial role in producing some of the heaviest elements in the universe. For decades, scientists believed that these super-heavy elements like gold and platinum could only be forged in the extreme heat and pressure of a massive cosmic collision between two neutron stars. However, new research suggests that magnetars with their enormous magnetic fields and volatile surfaces might also be heavy element factories capable of producing the universe's bling. And maybe they've been doing it all along. Magnetars are among the strangest objects in the cosmos. Even though they're just a few miles across, they pack about twice the mass of our Sun. That makes them incredibly dense. A teaspoon of matter from a magnetar would weigh more than a mountain. And while other neutron stars can have powerful magnetic fields, those of magnetars are truly mind-boggling. Their magnetic field strengths are so great that they actually pull themselves apart. Magnetars can lose up to 10% of their mass through these immense eruptions known as starquakes. And those quakes might be responsible for some of the gold found throughout the galaxy. But let's start at the beginning. When a massive star around 8 to 10 times larger than our Sun runs out of nuclear fuel, it collapses in on itself. That collapse propels the star's outer layers into space in a supernova explosion. What remains behind is an extremely dense core, so dense, in fact, that protons and electrons are forced together to form neutrons. That's what gives neutron stars their name. With no other force strong enough to stop them, these dead stars collapse until they're just a few miles across. In most neutron stars, the process of collapsing releases most of the star's energy. But in rare cases, a significant amount of energy can remain stored in the star's massive magnetic field. When that happens, the result is a highly magnetized neutron star, aka a magnetar. Within hours of their formation, these strange stars begin shaking. Their surfaces quake with gigantic flares that can release over 10 to the 44th power ergs of energy. To put that number in perspective, the total energy budget of the United States is about 10 to the 20th power ergs per year. These quakes aren't your typical star shakeup. They involve colossal eruptions of plasma and radiation that blast away part of the star's crust. Now we're talking about shaking things up on a galactic scale. As the crust gets blasted away, the star's atmosphere, which is composed mostly of hydrogen and helium, gets stripped away too. That creates a vacuum that allows matter from the star's interior to bubble up to the surface. This churning creates a gigantic cauldron of exotic matter, just waiting to cook up some heavy elements. Inside these stars, protons and neutrons work together to create nuclei for atoms. Normally, if a proton tried to combine with another proton, the positively charged particles would just repel each other. But inside a magnetar, the insane magnetic fields can overcome that electrostatic repulsion, forcing the protons together and creating a neutron. This process is called neutron drip because the neutrons literally drip off the protons. Since neutrons don't carry an electric charge, they're free to combine with more protons, creating heavier and heavier nuclei. That means under these extreme conditions, elements like gold and platinum can be formed without the need for a second star to collide with. It's like having your own personal bling factory in space. Now, just because something can happen doesn't mean it does. We still need to figure out if this is happening anywhere in our galaxy. Scientists recently reported they found evidence that magnetars might be responsible for some of the gold found throughout the Milky Way. But before we break out the champagne made of pure space gold, let's take a closer look at the study. The research was led by Wenlong Chen, an astrophysicist at the National Autonomous University of Mexico. In order to determine if magnetars played a role in producing heavy elements, the team had to find a way to analyze data from past gamma-ray telescopes. Magnetars are known to produce bursts of gamma rays, making them ideal candidates for hosting heavy element factories. But studying them is easier said than done. Gamma rays are highly energetic photons that can penetrate deep into space and even through the insides of planets. So observing these bursts requires specialized equipment. Luckily, several gamma-ray telescopes have been launched over the years. They just need someone to sift through the data. Enter the Swift Gamma-Ray Burst mission launched by NASA in 2004. Its primary mission was to detect and locate gamma-ray bursts. But after discovering over 500 bursts, the mission evolved into a survey of the entire sky. After 17 years of scanning space, Swift provided a treasure trove of data for Chen and her team to explore. Using data from Swift, the researchers studied over 2,000 gamma-ray bursts looking for correlations with elements like gold and platinum. The idea was that if magnetars were producing these elements, then nearby galaxies should show a higher concentration of gold and platinum than galaxies without magnetars. After analyzing the data, the team discovered that galaxies with magnetars have roughly 10 times more gold and platinum than galaxies without them. This discovery suggests that magnetars might play a bigger role in producing heavy elements than previously thought. But this isn't the whole story. We need to confirm that these gamma-ray bursts came from magnetars and not some other unknown process. That's where NASA's upcoming Constellation of Imaging X-ray and Gamma-ray Surveyor, or COSI, comes in. COSI will conduct the largest and most comprehensive survey of the gamma-ray sky to date. The mission will focus on transients, meaning short-lived phenomena such as magnetar outbursts. The goal is to measure the location, time, energy, and intensity of gamma-ray bursts. This data will help scientists identify what kind of objects are producing these bursts and better understand how heavy elements are produced in space. Until then, it's important to remember that correlation doesn't always mean causation. Other processes, such as supernovae, can also produce heavy elements. So while this study is a promising step forward, more research is needed to confirm that magnetars are indeed the bling bosses of the universe. Still, if they are, that means that almost every galaxy in the universe could have its own private gold mine. Imagine the possibilities. With this new information, scientists will need to update models of how elements are created and distributed throughout the cosmos. It might even rewrite our understanding of how magnetars evolve. And who knows? Maybe one day we'll uncover the secret to making diamonds from neutron stardust. Thanks to a surprising discovery, scientists now know that magnetars, strange, volatile neutron stars, can shake themselves apart through colossal eruptions known as starquakes. And those quakes might play a key role in producing some of the heaviest elements in the universe. This finding has shaken up the scientific community and added a new chapter to our understanding of how elements form in space. But the bling doesn't stop there. New missions like NASA's COSI promise to shed more light on these explosive outbursts, helping us solve the mystery of the universe's bling factory. Even though we're light years away, we're all connected by the very stuff that makes us us. From the iron in our blood to the calcium in our bones, the periodic table of elements is the building block of life. And now we're learning that even the most precious metals might have originated in the violent, chaotic world of Magnetars. So next time you look up at the night sky, remember that those twinkling stars might be hiding some serious bling. Thanks for watching this SCI Show video.